Okay, so let's get started. So this class we're going to talk about the optical and aerodynamic size distribution measurements. So again, if we do a quick recap, in our last class we further discussed the scanning mobility particle sizer. We discussed how the response or the time response of the SMPS might affect the accuracy for the measurement, because if we're doing the scanning upscan or downscan of the voltage, then there's going to be a response time of the CPC that will kind of delay or advance the measurement at certain sizes, right? So because of that, we need to do some extra calculation in the data inversion so that we get the accurate size distribution. And we also mentioned that because of this lag in the time response, people come up with new instruments to do these measurements with higher time resolution. There are instruments that are using electrometers to collect charged particle concentrations, but as we mentioned earlier, that electrometers really have a low have a high concentration resolution, which means that they cannot, or I would say low concentration resolution, because they cannot measure concentration of very low values, right? So they have a high detection limit. So because of that, we still want to get back to the counting based on the condensation of growth, and that's where the fast integrated mobility spectrometer, or the FIMS, fits into the problem. And further, we discussed different types of miniaturized differential mobility analyzers and DMAs for basically measurements of much smaller sizes, right? When we're talking about the ion mobility distribution measurements. Okay, so in this class, we're going to start some new contents regarding the optical size distribution measurement and the aerodynamic size distribution measurement. We'll start with the optical measurement first. So in the optical measurement techniques, there are basically different techniques or different aspects that are involved. So first is the different regimes of the scattering, right? So you probably know that from the aerosol science technology class or other aerosol related class, that there are different regimes of the light scattering. So when the particle size is very small, for example, the particle size is much, much smaller than the lambda or the wavelength of the radiation, right? Then the particle scattering or the light scattering is in the Rayleigh scattering regime. And when the particle size is comparable to the wavelengths, I would say it's between 0.01 lambda or all the way to, let's say, 100 lambda, then the light scattering is in the mere scattering regime. And in this regime, there's going to be some non-uniform or strange behavior of the light scattering, right? And based on these different regimes, so we can develop different methods to detect particles, right? Further, this part that we didn't mention is that if the particle size is much, much larger than lambda, then we call this as the geometric scattering regime. Where the scattering light intensity is just proportional to the particle diameter squared, okay? So this is again going to the very uniform regime. So based on these different regimes of light scattering, we can develop instruments to measure the size distribution of the aerosols. And then we actually developed this instrument called optical particle counters, or OPCs, to measure the size distribution of particles based on light scattering. Okay, and further, in terms of this interaction between the light and the particles, there's uh, um, there's both scattering involved and absorption involved. So scattering plus absorption is actually the extinction of the light. Okay, from these optical measurements, we could determine the scattering coefficient and absorption coefficient of the aerosol samples. Okay, so first we'll talk about the scattering. So basically, scattering is how an aerosol can, or any particle can scatter light in all different directions. For example, this is an incident light, right? If we're just talking about a single, let's say a very narrow width of the light, and then it interacts with the particle, and the particle can actually direct the light in all different directions, right? And then it turns out that this scatter light intensity, right, which is a function of the theta in different angles here, okay? So it's a function of the diameter of the particle, the wavelength, and also the refractive index of the particle. It depends on the material as well, okay? And further, by doing the integration, people find out that the scattering efficiency, okay, so this is extinction efficiency, scattering efficiency is now, since you integrate it in all the angles, right, so you can represent them as a relatively big term here, okay, and then this term here. Okay, and further, this scattering, this extinction or scattering efficiency is related to how much or what is the intensity of the light that can transmit after you shoot them through a cloud of aerosols. Okay, so basically, this extinction of the light intensity, right, is going to be an integral of the extinction coefficient, extinction efficiency multiplied by the number concentration of the particles, and further considering the cross section area of these particles. So basically, you have a particle that scatter light, right? And then extinction efficiency or scattering efficiency is normalizing this scatter light intensity by the cross section area of the particle, because eventually it's the cross section area of the particle that's directly corresponding to this this beam of the light, right? So basically, when the particle size is much smaller than the wavelengths, okay, so we're talking about the Rayleigh scattering here. When the particle size is much smaller than the wavelengths, you could integrate this and to get an analytical solution of the scattered light intensity and the extinction light intensity, right? So further, people find out that the scattering efficiency is proportional to the let's say it's proportional to the lambda to the power of -4, and then absorption efficiency is proportional to lambda to the power of -1. Okay, and you can further see that this scattering efficiency or extinction efficiency is dependent on the m here, and m is the refractive index of the particle, which is further dependent on the chemical composition of the particles. Okay, that's the Rayleigh scattering. And when it's in the Mie scattering regime, where the particle size is comparable to the wavelengths of the incident light, then you can see that the extinction efficiency or scattering efficiency is going to show these oscillations here. And these different oscillations are actually because of the Bessel function. So basically, in the Mie scattering regime, you can also solve the scattered light intensity theoretically, and it's a combination of Bessel function that's creating these oscillation in different, let's say, as a function of different particle sizes. Okay, so basically for the Mie algorithm, it solves the electromagnetic field equations and predicts the scattering or absorption efficiency from the alpha, where alpha is a size parameter. Right, you can see alpha is somewhat proportional to the, or is actually proportional to the ratio between the particle size and the wavelengths. Right, the larger the particle size, the larger the alpha. Right? So you can predict the scattering and absorption efficiency from alpha and the refractive index, and then also predicts the phase function for perpendicular and parallel polarization. So basically, the scattering is happening in all the different directions, right? When the light is directly shining on the particle, there's scattering in both parallel to this page here, but also perpendicular to this page here. So there's scatter light going inside, there's scatter light coming outside as well. So basically the main results from this Mie scattering is that when the alpha value is much smaller than 1, basically means the particle size is much smaller than the wavelengths, it converges to the Rayleigh scattering, because you can see here, this is just directly, let's say this is a mono, let's say it's just directly increasing, right? There's no oscillation at all. So it converges to the Rayleigh scattering, where the scatter light or the extinction or scattering efficiency is just proportional to lambda to the power of -4, right? And then when the particles, or I would say it's proportional to the dp to the power of 4. You can see here the scattering efficiency is proportional to alpha to the power of 4, which is further proportional to dp over lambda to the power of 4. Right, so basically it's proportional to the dp to the power of 4. Okay, and then further, when the alpha, let's say, is much larger than 1, then you have this geometric scattering where the extinction efficiency is just a constant. It is 2. Okay, and then between 1 and 100, so basically this extinction efficiency is oscillating, right? There's fluctuation, and then it's also very sensitive to the particle size, the wavelengths, and the refractive index. Okay, so this is a solution coming out of the electromagnetic field equations. Okay, so here it's showing you the Mie scattering diagram. So basically it's the intensity of the scattered light in different directions, and this is parallel to this this page here. You can see where the particle size is relatively small, where it has a small alpha value, right, the size parameter. You can see the scatter light intensity is almost uniform in all directions. And when the alpha value is, let's say, further larger, right, in the intermediate range, you can see it's scattering light and starts to have these oscillations here. It depends on the theta value, it depends on the particle size, and also the refractive index, right? So this is further showing you the how the Mie scattering is dependent on the angle. Okay, so here we show that at different angles, it's going to give you this oscillations here, right? And you can see it also happens to the particles with or the measurement at different angles. So basically, using this optical scatter or the scattering mechanism, people created instruments to monitor the scatter light intensity. So for example, here is a system that monitors the scatter light intensity of when aerosols go through the laser section, right? So here, this is the section where it introduced the laser beam. And you can introduce the aerosols from here, and then also there are some sheaths there. So over this region, the aerosols will scatter light, and the scattered light is further collected by this curved mirror here, and further gets detected by the photodetector. So by relating the intensity of the light that's received over here, and further, as we said, it's basically an integration of the extinction coefficient and the number concentration particles, right? And and also the, let's say, the cross-section area, right? Pi d to the power of 2 divided by 4 dp dp, right? So by doing this calculation here, you could find out, or there are algorithms where you can find out how the size distribution looks like for the aerosols. Okay, so these are different types of the optical particle counters, and then regarding the size range that they could measure how many channels for the particle sizing, and then what are the angles they're using, sample flow rate, and then also the maximum concentration. So you can see that for these OPCs, they have a limited size range, right? This is showing in micrometers. So they cannot really see particles below 0.1 micron. Okay, maybe for this instrument it can, but it's actually just above 90 nanometers, right? And the reason is that the scatter light, or the scattering efficiency, as we said, is proportional to the particle size to the power of 4, right? So you can see when the particle size is very small compared to the mean free path. Here we're talking about particles of sizes of around 100 or below 100 nanometer. And then normally when we use the OPCs, we use the laser in the visible range, right? With the wavelengths in the visible range, which means that the lambda is in the hundreds of nanometers. Let's say from 500 to, or from 300 to 600, right? So this means that the scatter light intensity is in the is close to the Rayleigh regime, and further, the scatter light intensity is proportional to the particle size to the power of 4. And this means that the scatter light intensity is going to be strongly dependent on particle size. And for the smaller particles, they cannot scatter much light, right? So that's why the OPCs are limited for mostly supermicron particles, right? Or at least, let's say, above 100 nanometers. And further, for these measurements, since they're using the optical methods, right? So basically the size that's derived from these measurements is also called the optical size. Right? It's related to the scatter light intensity. So there isn't a good way to directly, or we cannot directly compare the optical size with the mobility size, or let's say the aerodynamic size that we introduced earlier in the class, right? So further here, you can see that this is showing you the OPC, the retrieved signal as a function of the particle diameter. So as we said, the scatter light intensity, let's say in the Rayleigh regime, is proportional to particle size to the power of 4, and in the geometric regime, is proportional to 2, right? And further, the scatter light intensity can be calculated by the integral, right, of the Q multiplied by pi dp squared, right? And then over 4 multiplied by n, right? That's the size distribution. So you can see that if we assume certain, let's say the particles have a uniform size, okay, and have the same concentration, right? So the scatter light intensity then is going to be proportional to the dp to the power of 6 in the Rayleigh regime, and then in the geometric regime, then it's going to be proportional to the particle size to the power of 2. And you can clearly see that in this diagram here, right? When the particle size is small, if we plot the slope in the log scale, right, the slope is going to be 6, and here the slope is going to be 2. Okay, and these are measurements of particles of different chemical compositions. So people actually also use these OPCs for airborne particle measurements. So instead of housing the laser into an instrument, you could even put them into a probe that's hanging outside the, let's say, a research aircraft, right? So in this way, the air is just directly going through. I think it might be this probe here, okay? So FSSP is one example of the probes that's doing this real-time light scattering methods, light scattering characterizations. The full name for the FSSP is Forward Scattering Spectrometer Probe. What happens is it has 2 probes, and then basically one probe will shine a laser through the air that's between these 2 probes, right? That's the air going through these 2 probes, and then the other one contains the optics and then also the let's say the photodiode that collects the scatter light signal. And further, by using the scattering efficiency, and then there's a correlation between the scattering light intensity and the particle diameter, you can further calculate what is the size distributions of the particles. Okay, so a more commonly used, let's say, laboratory scale instrument that monitors the optical properties or the scattering efficiency of the particles is called the nephelometer. And TSI has a version of the nephelometer, that's TSI 3563. It's using a three wavelengths characterization method. Okay, so what happens is that inside the nephelometer, the aerosols are being introduced here. So as you can imagine, the aerosols will form a stream over here, and then they will exit from here, then go from here, right? And in the middle here, you have a lamp that shines on the aerosols. So because of light scattering, right, so particles are going to scatter light in all different directions, and there will be a stream of the light that will go through the tiny aperture here, or tiny hole here, and further get collected by these photodiodes. And further, for these photodiodes, they're screening out specific wavelengths of the light. So you characterize the scattering property of the aerosols in different wavelengths regimes. So you have the red regime, the green regime, and blue one. Okay, and as you can see, this is again an integral of all the aerosol, let's say the integral of all the, let's say, particles of different sizes, scattering coefficient, and then also scattering angles, right? So for example, here, when the particles is located over this location, only scatter light that's directly pointing to the aperture will get transmitted. And when the aerosol is here, then the light is being scattered in this angle and then further gets scattered here. So there is an algorithm to integrate the scatter light intensity and further find out what's the scattering coefficient or scattering efficiency of the aerosols. And for this instrument, it also has a shutter here, so which considers the best backscatter only. So the shutter here basically will block half of the, let's say, the radiation here, or this illumination here. So basically, when particle go through the system, there will be no particles getting scattering light in the forward direction. So there's only particles scattering light in the backward direction. So you can calculate the backscatter, basically limiting the angle for the measurement so that you can get more accurate scattering efficiency. Okay. So as we introduced earlier in this class, so nowadays there are newer instruments or newer devices to do air quality measurements. And one widely used instrument is called the low-cost air quality sensors. So low-cost air quality sensor has gained a lot of attention in recent years. So here I'm showing a basically the published articles that's related to low-cost air quality sensors. I just use low-cost air quality sensor as a keyword, and you can see over, let's say, the past 20 years or the past 10 years, there has been an exponential increase of the publications in this area, right? So low-cost air quality sensor, they have the advantage. So first, very important one is low cost, right? So conventional instruments to do air quality measurements, I would say they cost at least $10,000, right? And normally they need to be housed in well-established sampling stations or laboratories, where it limits the access of the data to the general public regarding how to do these measurements and to better understand their air quality. Right? If you think of an extreme, let's say if you don't have access to these instruments or data, the only sensor we have might be our nose or our eyes, right? And we want to provide some basic measurements to evaluate how the air quality looks like. So as you can see, because of that, people created different types of air quality sensors. And I would say most of these air quality sensors are using the light scattering methods. So here I'm showing you 3 different types of light scattering sensor, or let's say the low-cost sensors. And you can see they all involve some laser module here. And actually they're using the infrared LED, just light, typical light bulbs. And then the aerosols are being introduced through the sensors, right? And then there's a photodiode that's aligned on a different angle. So if it's placed at a different angle, then it's collecting the scatter light signal. Okay, so here I'm also showing you a sensor. This is the more, I would say, more popular sensor nowadays that's made by the plant tower. Okay, so for the plant tower sensor, it's similar. You have the airflow that's going through the channel here, and there's a laser, let's say LED light that shines the radiation through this channel here. And then for the laser diode, it's not placed at an angle, but actually it's placed at an angle. It's just below this laser here, right? The gas stream is going across, and then the sensor is placed on the bottom or directly on this plate here. So it's still collecting the scatter light signal. Let's say if the aerosols are directly above the sensor here, above the diode here, it's collecting the scatter light signal at 90-degree angle, right? But in actual situation, if the laser has some has a like a breath over there, right? It's going to collect aerosols, or it's going to collect scattered light signal from a range of angles. And from that range of angles, we could do similar types of integration to get the aerosol properties. So people use these sensors to conduct aerosol mass concentration measurements, and they want to directly report PM2.5 or PM10 out of these measurements. But how accurate are these sensors, right? We know that for the scattering or these local sensors, they are using scattered light signal. But we also mentioned that the scattered light signal is proportional to particle size to the power of 6, right? In the Rayleigh regime, and to the power of 2 in the geometric scattering regime, which means that if we want to get mass, it's not going to be directly proportional to mass, right? Mass is proportional to dp to the 3, to the third. So to test the performance of these sensors, we actually created different chambers to expose the sensors and standardize the instrument to aerosols of different chemical composition or size distribution. So if you're interested, you're welcome to read this paper here that's doing some laboratory evaluation calibration of the sensors. And based on the results, we can see that the sensors indeed responded pretty well against the particle mass. So here we were using a standardized instrument, or I would say a more expensive instrument for monitoring aerosol mass, that's called the side pack. And you can see that the sensor response actually quite correlate, or I would say the positive correlation between the sensor response and the side pack measured aerosol mass is pretty well. Right? You see this overall increasing trend, and we calculate the R-square values, and for some of the sensors, they can even achieve R-square value of close to 1, right? So again, this scatter light signal is not directly proportional to the particle mass, okay, based on the theory here. But there is indeed a positive correlation between the number concentration of the particles and also the mass also the size of the particles. Okay, so to better quantify this effect, there are different algorithms to calculate how the scatter light intensity is dependent on the particle mass. But overall, to do the measurement of the aerosol mass concentration using the local sensors, we need to consider different effects. For example, the effect of particle size, the effect of refractive index, which is further dependent on the chemical composition, the relative humidity, and also the temperature. So the size plays a role because, as we said, the scatter light intensity is directly a function of the particle size, right? And the refractive index also plays a role. RH plays a role because there is hygroscopic growth of the particles. We mentioned earlier in the tandem DMA measurements that the more humid environments will give you a larger particle size because of the hygroscopicity of the aerosols. They can absorb water and enlarge their size. So because of that, the scatter light intensity will also increase. The temperature will also play a role because there may be some volatile species in the particle that can shrink the particle size, and also the temperature can play a role on, let's say, the electronics of the sensors, right? So because of that, you can see there are many factors that we need to consider when evaluating the sensor response. So the question is, can we still use these sensors? Because there's always some doubts regarding the accuracy of the sensors. So I would say we can use them, but we have to understand their performance through sophisticated tests, just like how we treated other aerosol instruments. If we're going to, we plan to generate publishable data, right? We need to go through a rigorous calibration and also develop advanced algorithms to analyze the sensor data. So regarding the rigorous calibration, I recommend you to check the AQMD website, or they call this AQ Spec website. regarding the air quality sensor performance evaluating sensor. So basically nowadays, if there are new instruments or new companies manufacturing new sensors on air quality, not only particulate matter but also gaseous air pollutants, they will submit their sensors to the AQ spec so that their sensors can be evaluated, both being deployed in the laboratory calibration and also tested in the outdoor ambient sampling. So the AQ spec also manages several EPA stations so they can do the correlation or collocation measurements and also, let's say, deploy it for a longer period of time to look at the longer time response of the sensors. So nowadays, the PM sensors are being calibrated pretty well, and I would say that we can quite comfortably use these aerosol sensors as long as when we are maintaining them, right? So the more difficult problems are regarding are actually about the gaseous pollutant measurements, and even for these gas sensors, there can be some developments on the algorithms that make them suitable for regulatory monitoring. So here I'm showing you a figure that's basically comparing how the different types of calibration might improve the sensor response by reducing their precision error. So you can see there are laboratory calibration, machine learning calibration, and random forest calibration or algorithms. So you can see by using different algorithms, you can reduce the precision errors for these sensors. And at the same time, here the authors listed the requirements for different tiers for measurements, right? So for example, tier 1, that's for education information. You don't really require a very low error or precision error here, right? And tier 2 is hotspot identification, characterization, as long as you don't need to quantify these pollutant concentration, right? They don't need a high, I would say, high accuracy either. So the regulatory monitoring is the one that requires a very high accuracy, right? But you can see that through these improvements in the algorithms, we can further reduce the error here so that some of them can even be used for the regulatory monitoring, okay? So the problem is now how do we identify these advanced algorithms? So this will involve, again, the calibration where you collect the raw data and then to do these calibrations or develop these algorithms. Okay, so with these well-calibrated sensors and also very nice algorithms, we can start to deploy these sensors for air pollutant mapping. So we're interested in air pollutant mapping because we want to conduct more sophisticated exposure analysis, right? People, especially in South Florida, people are interested in the exposure disparity. But without a dense deployment of these air quality sensors, we would not be able to really understand what is the exposure in different neighborhoods or different areas of a city. And by using these air quality mapping data, we could also validate the transport models that are existing in the, let's say, the modeling field, right? So we could actually use these sensors to achieve these purposes. So right now, there are different applications of these air quality sensor mapping, air quality sensor deployment, right? So for example, we have done some work to deploy the sensor network in the machine shop, in the underground mine, and we have also been analyzing the air quality sensor deployment, let's say the mapping data within a city to further understand whether there are exposure disparities. Okay, so we talk about these scattering measurements. So what about absorption? So absorption is related to how much radiation is actually kept within the particle, right? So scattering is that the light is being scattered in different directions. So actually, one way to monitor the absorption is to monitor what's being totally extincted by the particle, right? For example, if you have some particles being collected onto the filter and you have a light source to shine upon these particles, right? You can measure what is the, let's say, what is the transmitted light intensity that is being extincted. And then also monitor the scatter light intensity surrounding the sample to characterize the scatter light intensity. and then the absorption is just the extinction minus the scattering. Okay, so based on this mechanism, there are different instruments being made, right? So one instrument is called the particle soot absorption photometer, or the PSAP. Okay, and then the other one called the multi-angle absorption photometry, or the MAP. So you can see the MAP is actually monitoring the scattering light intensity, and then to subtract the total extincted light signal by the scattered light intensity. Right. Another way to monitor the light absorption is using the photoacoustic method. So the photoacoustic method considers the light absorption that actually heats up the particle. So you can introduce a red laser here, right? So the laser incident beam is being absorbed by the particle, and then eventually it's heating up the particle. And if the particle heats up, then it's going to create a pressure change surrounding the particle. Basically, the pressure change is similar to the sound, right? The vibration of the, let's say, the air pressure, right? The sound wave is being generated in a similar mechanism, right? So basically, you create a disturbance of the pressure, air pressure here, that's equivalent to the sound. So that's why it's called the photoacoustic method. So you can monitor what is the response of the particle absorption, what is the response of the sound wave due to the absorption of the radiation here. Okay. So this is about the particle absorption method, and so the scattering and absorption method is a relatively short section, right? So basically, it's using these different scattering mechanisms, let's say in different regimes. And regarding the absorption, people can use the extinction minus the scattering to get the absorption signal, or use this photoacoustic method. So that's why for the absorption method, it's a relatively challenging method. But absorption plays a quite important role, because if, let's say, our Earth is covered by black carbon, then as we know, black carbon is going to absorb most of the radiation and acts similar to a black body, right? So because of that, there will be more radiation being trapped by the Earth, and we're going to have a net warming effect. So that's why the absorption is relatively important for us to understand the climate effects of the aerosols. So after the optical methods, so we're going to introduce a little bit about the aerodynamic size distribution measurement. So aerodynamic size distribution measurements will just rely on the inertia of the particles. We introduced in earlier that particles will have inertia, then because of that, they will have a stopping distance, right? And the stopping distance is just a product of the relaxation time multiplied by the initial velocity of the particles. So by using this mechanism, we can create an obstacle in front of a jet stream, right, or jet flow of the aerosols. So larger particles with larger inertia, they will just impinge onto the plate here. That's called impaction, right? And smaller particles can escape from the system. And we also said that it depends on a specific number called the Stokes number. So Stokes number is just the let's say stopping distance, tau u0, and then you divide that by a characteristic length. And it can be d, or diameter of the jet, or it can be the length of the plate, and so on, right? So basically, for different types of impactors, for example, for round impactors, we have this relationship that's correlating the specific size that can get classified, and also the geometries, or let's say the flow conditions of the impactor. And for rectangular impactors, you have this relationship here. Okay, so it is just being derived based on the definition between the Stokes number and the, let's say, the tau u divided by characteristic length, right? So basically, this is just the let's say the parameters that's related to the relaxation time. And generally, for these impactor stages, people define this Stokes 50 to represent the critical Stokes number, where has a 50% efficiency for collecting the particles. So for each impactor, it has a specific Stokes 50 number. And basically, these two equations tells you how to calculate the specific particle size corresponding to the Stokes 50 value. Okay. So you can see if we have a single stage of the impactor, we can collect particles above certain sizes, right? And you can actually assemble these impactors in series, and this is what we call the cascade impactor. So we achieve the classification of particles of different sizes. For example, for this stage, let's assume that it classifies particles of 10 micrometer, right? And the next stage, if we put in a stage that, let's say, collect particles above 10 micrometer, then on this stage, you just have particles between 8 to 10 micrometers. And for the next stage, you can have 6 to 8 and all the way down, right? So you can assemble an array of impactors. And that's how we call the, what we call the cascade impactors, okay? And especially here, there are different types of cascade impactors, and in the aerosol field, we use this moody impactor, which can classify particles or collect particles down to, let's say, tens of nanometers. There are several areas or major areas of the concern that we need to consider when we operate the cascade impactors. So one is the particle bouncing, right? If you have larger particles with larger inertia, they cannot really get collected by the stage, and they will bounce again and then go to the next stage. So because of that, people normally will apply some grease onto the stage here. So once the particles gets collected onto the impactor, it just stays there. We also need to worry about the overloading of the collected particles onto the impactor plate, because if you have too much of mass there, then you're going to change the aerodynamics and then further affect the particle collection. There's also interstate losses, where the particles might get lost onto the stage while they're being transported to the next stage through these impaction or interception processes. So as we introduced, if you try to classify really small particles on this end, what we need to do is we need to enhance the inertia of these particles. And to enhance the inertia of the particles, basically they need to have a longer relaxation time. And remember, in that equation, you have rho dp to the, let's say, we basically what we need to do is to increase the stopping distance of the particles, right? And then regarding the relaxation time, it's just rho p dp to the power 2, and then c divided by 18 mu, right? There isn't much change we can do towards the particle density or particle size. So the only thing we can do is to increase the velocity of the particles. But there's a limit regarding how much velocity we can provide. That is limited by how much flow we can send through the jet here. And then the flow, the maximum flow we can send through the jet is just the choked flow, which is under a Mach number of 1, right? It's just the speed of sound. And also, when it's operated near the speed of the sound, you also have the expansion of the air, right? Or the compression of the air. So the air cannot be assumed to be non-compressible anymore. So that's going to affect how the particles are being transported. There's going to be heat release and heat absorption. So regarding that, we need to use these low pressure impactors, right, to pull more flow, give the particles a higher velocity through the impactor or micro orifice impactor, right? You have very tiny holes for the particles to go through. So for these calculations, they are going to be different compared to the calculation we show here. And specifically on that, I would recommend you to follow Dr. Pratim Biswa's PhD thesis, which has been his major topic. So basically in his thesis, he specifically discussed what are the physics, what are the equations that's determining the particle collection, let's say under these enhanced velocity here, okay? So you can see we can create these cascade impactors with low pressures, and then specific for this instrument is called the electrical low pressure impactors, or the ELPI. This is also a commonly used instrument to monitor aerosol size distribution online. So what happens is that instead of measuring the particle mass after they're being collected. So on these stages, each stage actually collects to an electrometer, and further, the particles are charged by a corona discharger, which is a unipolar charger. And then it gives the particles sufficient charge that when they are being collected, they can transmit the current signal where you can further monitor the particle size distributions. And this is related to the aerodynamic size distributions. But we should notice that here, the particles being collected, actually, there can be issues associated with multiple charging, and also the let's say it cannot monitor particles with relatively low concentration because electrometers have limited resolution or limited detection for the particles of let's say of very low current, right, or particles of very small sizes. So this is showing you the response or the transfer function of the LP, the ELPI system, right? So we discussed the impactors for particle collection. There's actually a device called virtual impactor that instead of remove the larger particles, it concentrates the larger particles. So the way it works is that you have a two different nozzles or of different sizes, and then let's assume that we have larger particles and smaller particles here. And there's a flow introducing all of these particles through this first nozzle, and then there's exit flow that's coming out. But at the same time, you will pull flow from the outside, right? If we're smaller particles, then they have smaller inertia. They can just follow this exhaust flow here. But if they are larger particles, they have large enough inertia, so they will go through and then further get concentrated in this minor flow here. So this is showing you the response of the virtual impactor. So for particles of small sizes, they have let's say relatively large collection efficiency, right? And then for the larger particles, they actually can penetrate through the system, and then you could further, let's say, concentrate these aerosols and do some further analysis. And actually, during the COVID-19 pandemic, people tried to concentrate these larger particles because we know that these larger respiratory droplets contains more viruses, right? So by using the virtual impactor, you could, instead of sending a large flow of the ambient air for the environmental surveillance of these ambient aerosols, you can just use a smaller volume and then concentrate these droplets and further measure or to determine what is the quantity of the virus in the respiratory droplets. Okay, so there's also a device called the Aerodynamic Aerosol Classifier, which is also using the inertial inertial impaction or the inertia of the particles. So remember, we introduced the CPMA in our earlier class that's involving two concentric cylinders that's spinning, right? Over there, we said that it's using the balance between the drag force and the basically the centrifugal force, using the balance between the centrifugal force and the, let's say, the electrostatic force. So here, this is a variation of the CPMA system where you introduce the aerosols from the side of the inner cylinder, and then the two cylinders are spinning. So because of the spinning, the larger particles will get spun out. There's no electric field involved at all, right? So then only particles with specific inertia can get collected on the outside. And this is directly related to the inertia of the particles because no other forces are getting involved, right? So here is a short video that's showing you the mechanism of the aerodynamic aerosol classifier. So for this instrument, it can classify particles based on aerodynamic size down to 30 nanometers, right? Because now it really depends on how fast you spin these two cylinders, right? So if you have a larger speed, then these particles will have larger inertia and further get classified by the inlet over there, by the outlet over there. So again, if you want to do the size distribution measurement, you need to determine the transfer function of the instrument and further do the data inversion to measure or to convert it to the concentration. So compare this AAC, or the aerodynamic aerosol sizer, or aerosol classifier, to the SMPS. So you can see AAC has some good advantages, right? One advantage is that there's no charging involved. If there's no charging, then you don't need to consider the charging efficiency of particles with smaller sizes. Remember, regarding the particle charging, right, for particles of smaller sizes, their charging efficiency is very low, which means that the SMPS needs to consider this correction, this charging effect, when the particle size is small. For example, SMPS detect one particle at 10 nanometer, but actually it can be 100 or even 1,000 particles because the charging efficiency is low. But for the AAC, since it doesn't involve particle charging, you can directly measure the number of the particles coming out of it, right? So classified particles are being detected by the CPC. It directly reflects what's the actual concentration of the particles. Of course, the data inversion process is going to be a little bit more complicated because now you don't have like a fixed triangular shaped transfer function in this system, okay? So finally, I want to introduce the aerodynamic particle sizer, right? So aerodynamic particle sizer is basically, I would say, a commonly used instrument to monitor the aerosol size distribution in the supermicron range. So it works in a way that it introduces the aerosols through two nozzles, through a nozzle, and then there are two laser beams that basically characterize what is the time of flight, how much time it needs for the particles to go through these two laser beams or two laser sheets. Okay, so if you consider the equation regarding the particle movement, right, according to the Newton's second law, you're going to have the change of the velocity is related to the drag force, right? That's directly limited by the drag force. The larger particles, they move slower, and then their drag force is larger, right? Because there is a difference in the ambient velocity and the actual velocity of the particles. So basically, for particles with the same inertia, they're going to have the same acceleration and the same detection time, the same time of flight, right? So by analyzing the time of flight, you could back calculate, right? So because these equations are directly analytically solvable, you could directly calculate what is the aerodynamic size of the particles. So here I just want to mention that the measurement of the APS really depends on what type of material you're trying to measure, okay? So if you're measuring solid particles, then you don't see much of a problem. But when you're sizing droplets, then droplets can have different shapes, right? So for example, if you have a droplet that has a low surface tension, then when it goes through this high-speed nozzle, they're going to have different shapes, and a different shape will involve different drag force, okay? So if the drag force is different, then even if the droplet and the spherical, let's say solid particles have the same spherical physical size, then when they go through the nozzle here, they're going to have different time of flight, right? So because of that, the particle surface tension is going to affect how the particle is going to be detected in the APS. And you can see that if you're talking about different types of liquid particles, right, the larger the droplet, then the more size shift you are going to see in the APS. So this is something we need to pay attention when we do the aerodynamic size distribution measurements with the APS. Okay, okay, so that's it for this class. And this class we mainly discussed the optical size distribution measurement and the aerodynamic size distribution measurements. All right, so feel free to let me know if you have any questions. Thank you.